In the autumn of 2019, high on the summit of Mauna Loa in Hawaii, a robotic telescope sweeps its electronic gaze across the constellation Ursa Major. The night air moves thin and cold at 13,000 feet above sea level, where the atmospheric pressure drops to barely 2/3 that of the beaches below. Here, where ancient volcanic rock meets the clarity of space, the Asteroid Terrestrial Impact Last Alert System. ATLAS methodically photographs the same patches of sky night after night, searching for objects that move against the fixed stars. The telescope operates with mechanical precision, its mirror collecting photons that have travelled distances so vast that human language struggles to contain their meaning. Each night, it captures millions of stellar positions, comparing them against previous observations with software that never grows tired, never blinks, never allows sentiment to cloud its judgment. Most nights yield nothing remarkable, the same stars in the same positions, the same galaxies spinning at their measured distances, the same patient darkness between worlds. But on this particular evening in June, the system captures something unusual. A faint smudge of light that wasn't there 4 days before. The object appears as little more than a few pixels brighter than the surrounding sky, easily dismissed as instrumental noise or a cosmic ray striking the detector. Yet the automated algorithms flag it for human attention, and within hours, astronomers around the world begin the delicate process of confirming its reality. The object receives the mundane designation 2019 SL3, later renamed as C2019 L3IATLAS in honour of its discoverer. Such names carry no poetry, only the bureaucratic precision of scientific cataloguing. But as astronomers begin tracking its motion across successive nights, plotting its path against the background stars, they realise this visitor carries a profound secret hidden within the mathematics of celestial mechanics. The calculations reveal a hyperbolic orbit, not the elliptical path that binds solar system natives to our sun in their eternal dance, but the open curve of something passing through. The geometry tells an unmistakable story. This comet originates from interstellar space, making it only the third such object ever detected by human instruments. The first, ʻOumuamua, arrived like a tumbling stone, long and dark and silent. The second, 3I Borisov, behaved more like familiar comets, developing a proper tail as it approached the sun. Now 3IATLAS joins this sparse population of cosmic wanderers. Scientists estimate that 3IATLAS has travelled for millions of years through the galaxy's emptiness before encountering our solar system, a journey so extended that entire mountain ranges could rise and erode away during its passage between stars. It carries within its frozen nucleus the chemical fingerprints of whatever stellar nursery gave it birth, perhaps the debris cloud around a dying red giant whose outer layers drift into space like cosmic breath, or the turbulent disk surrounding a newborn star where planets haven't yet begun to coalesce from dust. The ice that forms its core condensed from vapours that never knew our sun's warmth. Every molecule within its nucleus formed under the gravitational influence of alien stars in molecular clouds where temperatures hover just a few degrees above absolute zero. The comet represents a fragment of some distant stellar system's history, preserved in frozen form and delivered across the light years like a message written in the universal language of chemistry. Yet already, even in the outer reaches of our solar system, where Jupiter's orbital distance seems close and Neptune remains a distant blue dot, something peculiar begins to happen. The comet develops a faint coma, the fuzzy envelope of gas and dust that typically appears only when comets venture much nearer to the sun. This premature awakening puzzles astronomers, who understand that most comets remain dormant until solar radiation grows intense enough to sublimate their frozen surfaces. Solar heating follows predictable patterns. At Earth's distance, sunlight delivers enough energy to melt ice rapidly. At Mars's distance, the process slows but continues. Beyond the asteroid belt, solar radiation weakens according to the inverse square law, each doubling of distance reducing heating by a factor of 4. By the time sunlight reaches Jupiter's orbit, it carries barely 4% of the intensity that warms our planet. Yet 3IATLAS stirs to life while still beyond Saturn's orbit, like a sleeper who wakes before dawn without knowing why. The mystery deepens as spectroscopic observations reveal the comet's composition. Light from the developing coma passes through Earth-based spectrometers, instruments that separate starlight into its component wavelengths like cosmic prisms. Each chemical element and molecule absorbs light at characteristic frequencies, creating a unique fingerprint in the spectrum. The analysis reveals something remarkable. Carbon monoxide begins streaming from the nucleus in quantities that suggest vast reserves of this exotic ice. On Earth, carbon monoxide represents danger, the colourless, odourless gas that can claim lives without warning, binding to blood cells more readily than oxygen and suffocating victims who never realise their peril. But in the deep cold of space, carbon monoxide freezes into crystals that preserve the chemical memories of alien star formation. This particular ice sublimates at temperatures far lower than water ice, which explains the comet's early awakening. Even the feeble warmth of distant sunlight proves sufficient to begin releasing carbon monoxide vapour into space. The process unfolds with geological patience. Individual molecules break free from the nuclear surface, accelerated by solar radiation pressure and carried away by the solar wind. Each escaping molecule represents a tiny fragment of the comet's mass. Lost forever to the vacuum, the nucleus slowly diminishes, grain by grain, like a sandcastle facing an incoming tide. Only the timescales differ, where ocean waves reshape sand in hours. Solar radiation reshapes comets across months and years. This gradual dissolution means that 3IATLAS faces an inevitable fate. Unlike the planets, which orbit our star for billions of years with minimal change, interstellar visitors burn brightest during their brief passage through the inner solar system. They arrive carrying the accumulated ice of millions of years in deep space, then surrender it all to our sun's warmth during a journey lasting mere months. The mathematics of this exchange seem almost wasteful, eons of preservation followed by rapid destruction, yet perhaps such waste represents a form of cosmic efficiency. The universe operates on scales that make human lifespans seem like momentary flickers. Mountain ranges rise and fall, species evolve and vanish, stars ignite and burn to ember, all while comets drift between stellar systems carrying their frozen archives. The brief moment when telescope and comet coincide in space and time allows astronomers to read messages composed in distant stellar nurseries, written in the universal alphabet of molecular bonds and crystalline structures, beyond Neptune's orbit, where sunlight arrives as little more than a suggestion of warmth. 3IATLAS continues its ancient journey through a realm that defies human comprehension. Here, in the outer reaches of our solar system, temperatures hover near absolute zero, that theoretical limit where molecular motion nearly ceases and matter approaches perfect stillness. The comet drifts through this cosmic desert, where a single photon from our distant sun carries barely enough energy to disturb a single ice crystal. The Kuiper belt stretches across this emptiness like a vast graveyard of primordial debris. Billions of objects orbit here in the solar system's twilight zone, chunks of rock and ice that never accumulated into planets, remnants from the violent birth of our cosmic neighbourhood 4.5 billion years ago. These native residents follow predictable elliptical paths, bound to our sun by gravitational threads that will hold them for eternity. They represent the local population, citizens of our solar system who have never known the influence of alien stars. But 3IATLAS moves among them like a foreign diplomat carrying credentials from distant courts. Its hyperbolic trajectory cuts through the Kuiper belt's orderly architecture with the confidence of something that owes no allegiance to our sun's gravity. The mathematics of its path reveal a visitor that will sample our solar system's hospitality briefly, then continue outward toward galactic spaces where our star appears as merely another point of light among countless others. The comet's nucleus measures perhaps a few hundred meters across, small enough to fit within a city block. yet containing enough frozen material to supply Earth's oceans with exotic molecules for millennia. This modest size reflects the delicate balance required for interstellar travel. Objects much larger would have been captured or destroyed by gravitational encounters during their journey between stars. Objects much smaller would have been swept away by stellar winds or disrupted by cosmic radiation. 3IATLAS represents the optimal size for cosmic wandering, substantial enough to preserve its structure across light years, compact enough to navigate the gravitational obstacles between stellar systems. Its surface appears darker than charcoal, absorbing sunlight with an efficiency that rivals the blackest materials known to science. This darkness results from millions of years of exposure to cosmic radiation, which gradually breaks down organic compounds and creates a layer of complex carbon molecules. The process resembles the slow formation of coal or petroleum on Earth, but extended across geological timescales and occurring in the absolute cold of interstellar space. Every grain of dust on the comet's surface carries the accumulated damage of its long journey impact craters from micrometeorites, chemical changes from cosmic ray bombardment, structural modifications from the freeze-thaw cycles of passing near different stars. Yet beneath this weathered exterior lies ice that preserves the chemical signature of its birth environment. Water ice forms the bulk of most comet nuclei, frozen into crystalline structures that trap other molecules like ancient amber-preserving insects. But 3IATLAS also carries more exotic frozen gases: carbon monoxide, carbon dioxide, methane, and nitrogen, each requiring different temperatures and pressures to condense from vapor into solid form. The relative abundances of these materials tell the story of whatever stellar nursery created this wanderer. The comet's early activation puzzles astronomers because it suggests an internal structure unlike anything found in our solar system's native population. Local comets typically remain dormant until they approach within Mars's orbital distance, where solar heating becomes sufficient to sublimate water ice at noticeable rates. But 3IATLAS begins outgassing while still beyond Saturn's orbit, where sunlight delivers barely 1% of the energy that reaches Earth's atmosphere. This premature awakening implies that the comet contains substantial quantities of highly volatile materials, substances that transition from solid to gas at extremely low temperatures. Carbon monoxide ice sublimates at -205 degrees Celsius, far below the sublimation point of water ice. Even the minimal heating provided by distant sunlight proves sufficient to begin liberating these exotic molecules into space, creating the faint coma that first alerted astronomers to the comet's unusual nature. The phenomenon unfolds with clockwork precision governed by the laws of thermodynamics. Solar radiation penetrates the comet's dark surface to depths of perhaps a few millimeters, warming subsurface ice just enough to trigger sublimation. The resulting gas pressure creates microscopic fractures in the nuclear material, allowing vapor to escape through a network of channels and vents. This process transforms the solid nucleus into a slowly expanding cloud of gas and dust, like watching a time-lapse film of a flower blooming across months instead of days. Each escaping molecule carries with it a tiny fragment of kinetic energy, creating a gentle rocket effect that slightly alters the comet's trajectory. This non-gravitational acceleration proves too small to detect with current instruments, but it represents one of the subtle ways that solar radiation shapes the paths of small bodies throughout our solar system. Over millions of years, such forces can gradually change a comet's orbit, sometimes enough to determine whether it eventually collides with a planet or escapes back into interstellar space. The irony of this situation seems almost deliberate. A visitor that has spent millions of years in the perfect preservation of deep space begins destroying itself the moment it encounters our sun's influence. The same solar radiation that allows telescopes to detect and study 3IATLAS also guarantees its eventual dissolution. Every observation represents a race against time, as the comet surrenders its accumulated ice to the vacuum of space in exchange for a brief moment of visibility. Observatory networks around the world begin coordinating their efforts, understanding that this opportunity may not arise again for decades. Professional telescopes in Chile, Hawaii, and Spain track the comet's position and brightness. Amateur astronomers contribute observations from suburban backyards and remote observing sites. Space-based telescopes provide measurements unfiltered by Earth's atmosphere. The global astronomical community mobilizes with the efficiency of researchers who understand that some phenomena offer only a single chance for study. The data streams in continuously photometry, revealing changes in brightness, spectroscopy identifying molecular components in the coma, astrometry tracking positional changes against background stars. Each measurement adds another piece to the puzzle of this interstellar visitor's nature and origin. Yet the fundamental mystery remains: why does 3IATLAS behave so differently from the thousands of comets previously studied by human astronomers? The answer may lie in the alien nature of its birthplace, a stellar environment where different physical conditions created ice compositions unknown in our solar system. Perhaps the comet formed in the debris disk around a more massive star, where higher temperatures and pressures allowed exotic ices to condense alongside familiar water ice. Or perhaps it originated in a molecular cloud with unusual chemical abundances, creating a nucleus rich in volatile compounds that sublime at temperatures far below those required for normal cometary activity. In the pre-dawn hours at observatories scattered across Earth's surface, astronomers peer through eyepieces and monitor computer screens, displaying the gradual brightening of 3IATLAS. The comet appears as little more than a fuzzy star to most telescopes, indistinguishable from the countless galaxies and nebulae that populate deep space photographs. Yet sophisticated instruments reveal subtle changes occurring night by night, fluctuations in brightness that follow no pattern familiar to comet researchers, spectral lines that strengthen and weaken according to mysterious rhythms. The Catalina Sky Survey in Arizona captures the comet's position with mechanical precision, adding each measurement to a growing database of observations. Thousands of miles away, telescopes in the Canary Islands and the Chilean Andes contribute their own data points, creating a global surveillance network that tracks 3IATLAS across the sky with unprecedented accuracy. This collaborative effort represents one of astronomy's quiet triumphs, researchers separated by oceans and time zones, working together to decode the secrets of a single cosmic wanderer. The comet's brightness varies in ways that challenge theoretical expectations. Most comets follow predictable patterns of illumination, growing steadily brighter as they approach the sun, and solar heating increases the rate of gas and dust production. But 3IATLAS displays irregular fluctuations that suggest a more complex internal structure. Some nights it appears notably brighter than predicted. Other nights it dims unexpectedly, as if internal processes have temporarily slowed or ceased entirely. These variations occur on timescales ranging from hours to weeks, implying multiple mechanisms operating within the comet's nucleus. Perhaps jets of gas emerge from specific locations on the surface, activated by solar heating of subsurface ice deposits. Perhaps the nucleus rotates with a period that brings different surface compositions into sunlight at regular intervals. Perhaps internal fractures create new pathways for gas escape, then seal themselves as subliming ice refreezes in deeper layers. Spectroscopic analysis reveals an even more puzzling phenomenon. The characteristic signatures of carbon monoxide and carbon dioxide appear and disappear in the comet's spectrum with periodicities that don't match any known rotational period. Sometimes these molecular fingerprints dominate the observations, suggesting massive outgassing events. Other times they fade to barely detectable levels, as if the comet has temporarily exhausted its supply of volatile materials. This behavior contrasts sharply with the steady, predictable outgassing observed in most comets. Familiar solar system residents like Comet Halley or Comet Hale-Bopp display brightness variations that correlate clearly with their distance from the Sun and their rotational periods. Their spectra show consistent molecular abundances that change gradually as different surface materials become exposed to solar heating. They behave like well-understood machines, following the laws of physics with reassuring predictability. But 3IATLAS operates according to different rules, as if its alien origin has endowed it with properties that don't conform to local expectations. the comet seems to possess an internal chemistry unlike anything found in our solar system's native population. Its ice contains molecular combinations that formed under conditions that never existed in our Sun's protoplanetary disk. Its nuclear structure reflects gravitational and thermal processes that occurred in the vicinity of foreign stars, under the influence of alien stellar winds and radiation fields. The mystery deepens when astronomers attempt to determine the comet's rotational period, a fundamental property that should reveal itself through regular brightness variations as different surface features rotate into and out of sunlight. Most asteroids and comets display clear rotational signatures, periodic fluctuations that allow researchers to calculate spin rates and sometimes infer surface topography, but 3IATLAS resists such analysis, showing brightness changes that appear almost random. This irregular behavior suggests several possibilities, none entirely satisfactory. Perhaps the comet tumbles chaotically rather than rotating around a stable axis, a condition that could result from collisions with interstellar debris during its long journey between stars. Perhaps its nucleus consists of multiple fragments held together by gravity so weak that solar heating disrupts the structure, causing pieces to separate and rejoin in complex patterns. Perhaps outgassing occurs so violently that rocket forces constantly alter the comet's spin state, preventing the establishment of stable rotation. Each hypothesis raises additional questions about the comet's internal composition and structural integrity. If 3IATLAS truly represents a gravitationally bound collection of fragments, then it offers a glimpse into the assembly processes that operated in its birth stellar system. If its chaotic tumbling results from interstellar collisions, then its surface should display impact craters and fracture patterns unlike anything seen on solar system objects. If explosive outgassing governs its behavior, then its nucleus must contain volatile materials in concentrations far exceeding those found in familiar comets. Ground-based observers push their instruments to theoretical limits in attempts to resolve surface details or detect signs of fragmentation. The Hubble Space Telescope contributes high-resolution images that reveal a slightly elongated nucleus surrounded by an asymmetric coma. Radio telescopes search for molecular emission lines that might indicate the presence of complex organic compounds. Infrared observatories measure thermal radiation to constrain surface temperatures and composition. Yet the fundamental puzzle persists. Why does this interstellar visitor behave so differently from every comet previously studied by human astronomers? The question haunts researchers who have devoted careers to understanding these primitive remnants of solar system formation. Comets typically represent time capsules, preserving conditions that existed during the earliest epochs of planetary formation. Their predictable behavior reflects the orderly processes that govern their creation in our Sun's protoplanetary disk. But 3IATLAS arrives carrying the chemical and physical signatures of alien star formation, processes that operated under different conditions and produced different results. Its irregular brightness variations may reflect compositional inhomogeneities created by stellar winds with different intensities than our Sun's. Its unusual outgassing patterns may result from ice structures that formed under gravitational fields, with different characteristics than those that shaped our solar system's residents. The comet represents a natural experiment in comparative planetology, a chance to study material that formed under completely different circumstances than anything found in our cosmic neighborhood. Every observation provides insights into stellar formation processes that operated billions of years ago in distant regions of the galaxy. Every spectrum contains information about the chemical evolution of interstellar space and the diversity of planetary system formation mechanisms, yet time works against the observers. Each day of study brings 3IATLAS closer to the Sun, where increasing solar radiation will accelerate its disintegration. The comet that puzzled scientists with its premature awakening will eventually surrender all its mysteries to the vacuum of space, leaving behind only photographs, spectra, and theoretical models. The window for detailed study remains open for months, not years, a brief opportunity to decode secrets that took millions of years to preserve during the journey between stars. The phenomenon begins subtly, almost imperceptibly, in the vast emptiness beyond Saturn's orbital realm. Here, where our Sun appears as merely the brightest star in a field of countless others, 3IATLAS experiences the first tentative caresses of solar radiation. The energy flux measures less than 1% of what reaches Earth's atmosphere, barely sufficient to warm a thermometer by a few degrees above the cosmic background temperature. Yet within the comet's nucleus, this minimal heating triggers processes that should not occur for millions of miles. Traditional comet theory predicts dormancy at such distances. Water ice, which comprises the bulk of most cometary nuclei, requires substantial solar heating to sublime at detectable rates. The sublimation curve for water follows well-established physics at the temperatures prevailing beyond Saturn's orbit. Water ice should remain frozen solid for millennia. Only when comets venture within the inner solar system, where Mars orbits our star, does significant water sublimation typically begin. This pattern has held true for thousands of observed comets over decades of systematic study. But 3IATLAS awakens like a sleeper responding to whispers rather than shouts. Telescopic observations detect the first traces of coma formation, while the comet remains farther from the Sun than Jupiter ever travels. This premature activity suggests internal processes that operate according to different rules than those governing familiar solar system residents. The comet behaves as if it contains materials that respond to energy inputs too weak to affect normal cometary ice. Spectroscopic analysis provides the first clues to this mystery. The characteristic absorption lines of carbon monoxide begin appearing in the comet's spectrum at distances where such emission should be impossible. Carbon monoxide ice possesses a sublimation temperature nearly 50 degrees lower than water ice, a difference that proves crucial in the extreme cold of the outer solar system. While water ice remains frozen solid, carbon monoxide ice begins its transition from solid to gas under the influence of even minimal solar heating. This discovery reveals 3IATLAS as a fundamentally different type of object than the comets native to our solar system. Local comets formed in the relatively warm environment of our Sun's protoplanetary disk, where temperatures favoured the condensation of water ice over more volatile materials. Carbon monoxide, methane, and nitrogen remained gaseous during most of the solar system's formation epoch, escaping to interstellar space rather than incorporating into solid bodies. Only in the coldest outer regions did these exotic ices condense, and even then in much smaller quantities than water ice. But 3IATLAS carries the chemical signatures of formation in an environment where such exotic ices could condense in abundance. Perhaps its birth stellar system possessed different thermal characteristics than our own, a cooler protoplanetary disk where carbon monoxide ice formed as readily as water ice forms here. Perhaps it originated in a molecular cloud with unusual chemical abundances, where carbon-bearing molecules achieved concentrations unknown in our solar neighbourhood. Perhaps its nucleus assembled from materials ejected by a dying star, carrying with it the exotic chemistry of stellar evolution processes. The implications extend beyond simple compositional differences. If 3IATLAS truly contains substantial quantities of carbon monoxide ice, then its internal structure must differ dramatically from familiar comets. Carbon monoxide sublimates more readily than water ice, creating internal gas pressure that could fracture the nucleus or create complex networks of subsurface cavities. The comet's irregular brightness variations might reflect this dynamic internal structure, as gas pressure builds and releases according to the thermal cycles imposed by solar heating. Each rotation period brings different surface compositions into sunlight, triggering outgassing events of varying intensity. Regions rich in carbon monoxide ice would respond immediately to even minimal solar heating, producing jets of gas and dust that brighten the comet's coma. Regions dominated by water ice would remain inactive until much later in the comet's approach to the Sun. This patchwork of surface compositions could explain the erratic brightness fluctuations that puzzle observers. The phenomenon creates a form of cosmic irony. An object that has preserved alien ice compositions across millions of years of interstellar travel begins destroying itself the moment it encounters our Sun's influence. The same solar radiation that allows telescopes to detect 3IATLAS also guarantees its eventual dissolution. Every photon that illuminates the comet for observation simultaneously contributes to its destruction, like reading a manuscript that crumbles with each page turn. This premature awakening also reveals the delicate balance required for interstellar objects to survive their journeys between stellar systems. Most comets that escape their birth systems would likely disintegrate during passage through the galaxy's radiation fields and gravitational perturbations. Only objects with precisely the right combination of size, composition, and structural integrity can complete such journeys intact. 3IATLAS represents a successful example of this improbable survival, a cosmic message that has travelled across light years to reach our telescopes. The comet's early outgassing creates observational opportunities unavailable for most solar system residents. Because 3IATLAS begins producing a detectable coma at vast distances from the Sun, astronomers can study its composition and behaviour across a much wider range of solar heating conditions than typically possible. This extended baseline of observations provides unprecedented insights into how exotic ice compositions respond to gradually increasing energy inputs. Professional observatories worldwide coordinate their efforts to capture every detail of this extended awakening process. The European Southern Observatory's Very Large Telescope in Chile obtains high-resolution spectra revealing molecular abundances in the developing coma. The Keck Observatory in Hawaii contributes infrared observations that constrain surface temperatures and thermal properties. Space-based telescopes provide measurements uncontaminated by Earth's atmospheric absorption lines. Each observation adds another piece to the puzzle of 3IATLAS's unusual behaviour. The comet's brightness increases more rapidly than predicted by standard models, suggesting outgassing rates that exceed theoretical expectations for objects at such distances from the Sun. Its spectrum shows molecular lines that vary in intensity over periods ranging from hours to days, implying dynamic processes within the nucleus that operate faster than simple solar heating can explain. These rapid variations hint at internal mechanisms that remain poorly understood. Perhaps thermal waves propagate through the comet's interior faster than expected, triggering subsurface ice sublimation in cascading patterns. Perhaps structural instabilities cause sudden releases of trapped gases, producing episodic brightening events. Perhaps electromagnetic effects associated with the comet's passage through the solar magnetic field contribute to heating processes beyond simple radiative warming. The mystery deepens as 3IATLAS continues its approach toward the inner solar system. Each week brings new observations that challenge existing theories about comet behaviour and composition. The visitor from interstellar space refuses to conform to local expectations, behaving instead like an ambassador from a cosmic realm, where different physical processes govern the formation and evolution of small bodies. Its premature awakening represents just the first act in a drama that will unfold over months as the comet encounters increasingly intense solar radiation during its passage through our stellar neighbourhood. In laboratories scattered across Earth's continents, spectrometers dissect the light from 3IATLAS with surgical precision, separating each photon according to its wavelength like cosmic archaeologists examining artifacts from an alien civilization. These instruments operate on principles that would seem like magic to earlier generations' devices that can identify specific molecules across billions of miles by analysing the precise frequencies at which they absorb starlight. Each absorption line in the spectrum tells a story written in the universal language of quantum mechanics, revealing the chemical composition of materials that formed under distant suns. The process unfolds with methodical patience. Starlight from the comet passes through Earth's atmosphere, where water vapour and oxygen molecules remove certain wavelengths before the signal reaches ground-based telescopes. Sophisticated correction algorithms compensate for these terrestrial contaminations, subtracting the familiar signatures of our own planet's chemistry to reveal the pristine spectrum of the interstellar visitor. What remains represents pure information about the comet's composition molecular fingerprints that carry memories of its alien birthplace. The initial spectroscopic results reveal familiar molecules arranged in unfamiliar proportions. Water vapour appears in the expected quantities, creating the characteristic absorption lines that have marked cometary spectra for decades. But carbon monoxide dominates the observations to a degree unprecedented in solar system comets, producing emission lines so strong they initially confused automated analysis software designed to process more typical compositions. The relative abundance of carbon monoxide to water approaches ratios never before observed in natural objects within our cosmic neighbourhood. This chemical signature suggests formation conditions dramatically different from those that created our solar system's native population. In our Sun's protoplanetary disk, carbon monoxide remained gaseous at the temperatures where most comets condense from the primordial nebula. Only in the outermost regions, beyond Neptune's current orbit, did conditions become cold enough for significant carbon monoxide ice formation. Even there, water ice dominated the condensation process, creating comet nuclei with carbon monoxide abundances measured in percentages rather than the near-equal ratios observed in 3IATLAS. But the spectrum reveals additional mysteries that challenge theoretical expectations about interstellar chemistry. Nitrogen molecules appear in quantities that exceed predictions for objects formed in typical stellar environments. On Earth, nitrogen comprises nearly 80% of our atmosphere, but in space it typically remains locked in more complex organic compounds rather than existing as simple diatomic molecules. The abundance of molecular nitrogen in 3IATLAS suggests formation in an environment where this normally reactive element could freeze out as pure ice. Carbon dioxide lines provide another puzzle piece that doesn't fit standard models of comet formation. Most solar system comets contain carbon dioxide in modest quantities, typically comprising a few percent of their nuclear ice. But 3IATLAS displays carbon dioxide abundances that rival its water content, suggesting formation in a carbon-rich environment where this molecule could condense as readily as water ice condenses in our solar system. Such conditions might exist in the aftermath of stellar explosions, where carbon-bearing gases expelled by dying stars could create unusual chemical environments. The isotopic ratios encoded in these spectral lines offer additional clues about the comet's origin. Different stellar processes produce isotopes in characteristic proportions, creating signatures that persist for billions of years after the original nuclear reactions cease. Preliminary measurements suggest that 3IATLAS contains isotopic ratios unlike anything found in solar system materials. Subtle variations in carbon-13, nitrogen-15 and oxygen-18 abundances that point toward formation in a stellar environment with different nuclear processing history than our Sun. These isotopic signatures represent some of the most profound information available about the comet's past. Unlike chemical compositions, which can change through sublimation and thermal processing, isotopic ratios preserve the nuclear fingerprints of whatever stars contributed material to the comet's formation region. Each isotope tells the story of specific nuclear reactions carbon-13 produced in the cores of massive stars, nitrogen-15 created during explosive nucleosynthesis events, oxygen-18 formed in the helium-burning shells of evolved stars. The combination of unusual molecular abundances and exotic isotopic ratios paints a picture of 3IATLAS as a messenger from a stellar environment unlike our own. Perhaps it formed in a molecular cloud enriched by the explosive death of massive stars, where carbon and nitrogen compounds achieved concentrations impossible in more typical interstellar environments. Perhaps its birth system developed around a star with different mass and metallicity than our Sun, creating thermal and chemical conditions that favoured the formation of exotic ice compositions. Yet questions remain about how such unusual materials could survive the journey between stellar systems. Cosmic radiation should gradually alter molecular structures over million-year timescales, breaking apart complex compounds and creating more stable configurations. Collisions with interstellar dust particles should erode surface layers, exposing deeper materials to space weathering processes. Gravitational encounters with rogue planets or brown dwarf stars should disrupt loosely bound structures, potentially destroying objects with unusual compositions. The survival of 3IATLAS's exotic chemistry suggests either remarkable preservation mechanisms or relatively recent ejection from its birth system. Perhaps the comet's nucleus possesses unusual structural properties that protect internal ice from cosmic radiation damage. Perhaps it travelled along a path through space that avoided the most destructive interstellar environments. Perhaps its journey time measured thousands rather than millions of years, insufficient for significant alteration of its original composition. Spectroscopic monitoring reveals temporal variations that add another layer of complexity to the comet's behaviour. The strength of carbon monoxide emission lines fluctuates over periods ranging from hours to days, suggesting dynamic processes within the nucleus that operate much faster than simple solar heating can explain. Sometimes the emissions strengthen dramatically, as if sudden releases of trapped gas create temporary brightening events. Other times they fade to barely detectable levels, implying cessation of outgassing from carbon monoxide-rich regions. These rapid variations challenge models of comet outgassing that assume gradual, steady responses to solar heating. Traditional theory predicts that sublimation rates should change smoothly as objects approach the Sun, following predictable thermal curves based on solar flux and nuclear composition. But 3IATLAS displays behaviour more reminiscent of geysers than steady evaporation episodic bursts of activity, separated by periods of relative quiescence. The phenomenon might reflect internal structural instabilities created by the comet's unusual ice composition. Carbon monoxide ice sublimates more readily than water ice, potentially creating subsurface cavities where gas pressure can build until structural failure releases it in sudden bursts. Alternatively, the comet's nucleus might consist of distinct regions with different compositions, each responding to solar heating according to its own thermal properties and volatile content. Radio telescopes contribute additional spectroscopic information by detecting molecular emission lines invisible to optical instruments. These observations reveal the presence of complex organic molecules methanol, formaldehyde, hydrogen cyanide that suggest chemical processes operating within the comet's coma. Such molecules form when solar ultraviolet radiation breaks apart simpler compounds, creating reactive fragments that recombine into more complex structures. The specific molecular species detected provide insights into the original ice composition and the photochemical reactions occurring as the comet approaches the Sun. Each new spectroscopic observation adds detail to the portrait of 3IATLAS as a chemical time capsule from an alien stellar environment. Its unusual molecular abundances and isotopic ratios preserve information about stellar nuclear synthesis processes that operated billions of years ago in distant regions of the galaxy. Its dynamic outgassing behavior reveals internal structures created by formation conditions unlike anything that occurred in our solar system's history. As 3IATLAS continues its passage through the solar system's outer reaches, something remarkable begins to unfold. In the space surrounding its nucleus, the gradual emergence of not one tail, but two distinct streams of material that paint separate stories across the cosmic void. This dual manifestation represents one of nature's most elegant demonstrations of how different physical processes can operate simultaneously on the same celestial object, each responding to solar influence according to its own particular laws of physics. The dust tail emerges first, a gossamer stream of microscopic particles liberated from the comet's nucleus by subliming ice. Each grain measures only micrometers across, smaller than the width of human hair, yet collectively they create a luminous arc that stretches millions of kilometers behind the comet's path. Solar radiation pressure pushes these particles away from the Sun with gentle but inexorable force, like cosmic wind sculpting clouds from solid matter. The dust tail follows the comet's orbital trajectory, creating a graceful curve that traces the path of 3IATLAS through space. Simultaneously, a second tail develops the gas tail, composed of ionized molecules stripped of electrons by solar ultraviolet radiation and magnetic fields. This plasma stream behaves according to different rules than the dust tail, responding not to radiation pressure, but to the solar wind, that continuous flow of charged particles streaming outward from our star at speeds exceeding 1,000,000 miles per hour. The gas tail points directly away from the Sun regardless of the comet's motion, creating a straight blue-green arrow that shifts direction as 3IATLAS moves along its hyperbolic orbit. The contrast between these two tails reveals the complex physics governing small body interactions with solar radiation and magnetic fields. Dust particles, being electrically neutral and relatively massive, respond primarily to photon momentum, the tiny push exerted when sunlight bounces off their surfaces. This force operates uniformly in the direction away from the Sun, creating the curved dust tail that follows orbital mechanics, like a visible record of the comet's passage through space. But ionized gas molecules experience electromagnetic forces thousands of times stronger than radiation pressure. The solar wind's magnetic field lines grab these charged particles and sweep them away at high velocity, creating the straight gas tail that always points anti-solar regardless of orbital geometry. The result resembles a cosmic weather vane, constantly indicating the direction of solar wind flow, while the dust tail traces the historical path of the comet's journey. In 3IATLAS, these two tails develop with unusual characteristics that reflect the comet's alien composition. The dust tail displays colours slightly different from those typically observed in a solar system comets. Subtle shifts toward redder wavelengths that suggest mineral compositions unlike familiar silicate grains. Spectroscopic analysis reveals that the dust contains carbon-rich particles, possibly organic compounds formed in the reducing environment of the comet's birth stellar system. These particles absorb and scatter sunlight differently than typical cometary dust, creating the distinctive coloration that marks 3IATLAS as a visitor from foreign cosmic realms. The gas tail presents even more dramatic anomalies. Its brilliant blue-green fluorescence results from carbon monoxide and carbon dioxide ions, excited by solar ultraviolet radiation. But the relative intensities of different emission lines suggest molecular abundances unlike anything observed in local comets. Carbon monoxide dominates the spectrum to such a degree that the tail appears almost monochromatic in certain wavelength ranges, creating a plasma stream with spectral characteristics never before recorded in detail. This compositional uniqueness creates observational opportunities unavailable with typical solar system comets. Because 3IATLAS produces such abundant carbon monoxide outgassing, its gas tail becomes visible at distances where most comet tails remain undetectable. The enhanced emission allows astronomers to study plasma physics and magnetospheric interactions under conditions impossible to replicate with local objects. The comet essentially provides a natural laboratory for investigating how exotic gas compositions interact with solar wind magnetic fields. The two tails also evolve at different rates as 3IATLAS approaches the Sun. Solar heating gradually increases the rate of dust production, causing the dust tail to grow longer and brighter over weeks and months. But the gas tail responds more dynamically, strengthening and weakening according to variations in solar wind intensity and magnetic field orientation. Sometimes the gas tail dominates visual observations, creating a brilliant streak across astronomical photographs. Other times it fades to near invisibility while the dust tail maintains steady luminosity. These temporal variations provide insights into the internal structure and composition of the comet's nucleus. Regions rich in volatile ices contribute primarily to gas tail formation, while areas containing more refractory materials produce the dust component. The relative strength of each tail at different times suggests a heterogeneous nucleus with patches of varying composition distributed across the surface. As solar heating penetrates deeper into the nuclear interior, different ice reservoirs become activated, altering the balance between gas and dust production. The geometry of the two tails creates spectacular visual displays when viewed from Earth's perspective. Sometimes the orbital mechanics align so that both tails appear side by side, creating a forked appearance like a cosmic tuning fork. Other times the dust tail curves across our line of sight while the gas tail points directly toward or away from Earth, creating complex overlapping patterns that challenge photographers attempting to capture the comet's full structure in single exposures. Professional observatories employ specialized techniques to separate the contributions of dust and gas components in their observations. Polarization filters reveal the dust tail's scattered sunlight while suppressing gas emission. Narrow-band filters isolate specific molecular emission lines, characteristic of the gas tail, while blocking continuum radiation from dust. These technical approaches allow researchers to study each component independently, revealing physical processes that would otherwise remain hidden in the combined light of both tails. The dust analysis proves particularly rewarding, as microscopic particles liberated from the nucleus carry direct samples of material formed in the comet's birth stellar system. Each grain represents a fragment of primordial solid matter that condensed from vapors in an alien protoplanetary disk, preserved frozen for millions of years during the journey between stars. Spectroscopic examination of this dust provides information about chemical conditions, temperatures, and pressures that existed during planetary formation around distant stars. The gas tail offers complementary insights into the volatile chemistry of the comet's interior. Different molecular species sublime at characteristic temperatures, creating a natural chromatography experiment as 3IATLAS approaches the Sun. Carbon monoxide appears first, followed by carbon dioxide, then water vapor, each contributing its distinctive spectral signatures to the growing tail. The sequence and timing of these molecular appearances reveal the layered structure of exotic ices within the nucleus. Magnetic field measurements obtained by space-based instruments reveal how the solar wind interacts with the comet's ionized coma and tail. The charged particles create electrical currents that generate their own magnetic fields, producing complex electromagnetic phenomena as the plasma tail develops. These interactions provide natural experiments in space physics, demonstrating principles of magnetohydrodynamics under conditions impossible to achieve in terrestrial laboratories. The twin tails of 3IATLAS thus serve as cosmic instruments, each revealing different aspects of the comet's nature and history. The dust tail preserves solid samples of alien star formation, while the gas tail demonstrates exotic ice chemistry in action. Together they create a comprehensive portrait of an interstellar visitor whose dual nature reflects both its ancient origins and its dynamic response to our Sun's influence. As the comet continues its approach toward the inner solar system, both tails will grow longer and more complex, writing the story of this cosmic wanderer across millions of kilometers of space. The orbital mechanics that govern 3IATLAS unfold with mathematical precision, each calculation revealing the elegant architecture of celestial motion that binds the universe together. In observatories worldwide, astronomers feed positional measurements into computers that solve differential equations describing gravitational interactions between the comet and every significant mass in the solar system. The resulting trajectory emerges not as a simple curve, but as a complex dance choreographed by invisible forces that operate across millions of kilometers with perfect consistency. The fundamental geometry proves unmistakable, a hyperbolic orbit that opens toward infinity, rather than closing upon itself like the elliptical paths that confine solar system natives to eternal servitude around our Sun. This mathematical signature distinguishes 3IATLAS as unequivocally interstellar in origin, a visitor whose gravitational allegiance belongs to no single star but to the galaxy itself. The hyperbola's precise parameters encode the comet's velocity and approach angle when it first entered our solar system's gravitational sphere of influence, preserving information about its trajectory through interstellar space. Calculating these orbital elements requires extraordinary precision, as tiny measurement errors can propagate into enormous uncertainties when projected across astronomical distances and timescales. Each telescopic observation contributes another data point to the mathematical model, gradually refining estimates of the comet's exact path through space. Professional observatories coordinate their efforts to obtain measurements spanning weeks and months, creating a baseline sufficient to determine orbital parameters with confidence levels approaching statistical certainty. The comet's velocity at solar system entry exceeded 11 kilometers per second relative to the Sun, fast enough to cross the continental United States in less than 7 minutes. yet barely sufficient to escape our star's gravitational embrace after completing its passage through the inner planets. This velocity places 3I-ATLAS at the lower end of the expected range for interstellar objects, suggesting either a relatively nearby origin or ejection from its birth system with minimal excess speed beyond escape velocity. The mathematical analysis reveals that 3I-ATLAS approached our solar system from the direction of the constellation Lynx, arriving along a trajectory inclined 60 degrees relative to the ecliptic plane where Earth and other planets orbit. This steep inclination indicates that the comet's birth system possessed orbital characteristics dramatically different from our own, perhaps a collection of planets orbiting in planes tilted relative to their star's equator, or debris ejected during violent dynamical interactions between multiple stellar companions. As the comet penetrates deeper into our solar system, gravitational perturbations from the giant planets begin subtly modifying its trajectory. Jupiter's massive gravitational field, equivalent to more than 300 Earth masses, exerts the strongest influence, bending the comet's path by amounts measurable only through careful analysis of positional observations spanning many weeks. Saturn, Uranus, and Neptune contribute smaller but still significant perturbations that must be included in accurate orbit calculations. These gravitational effects create opportunities to probe the internal structure of 3I-ATLAS through techniques unavailable for most astronomical objects. As the comet passes near massive planets, tidal forces attempt to stretch its nucleus along the direction connecting it to the perturbing body. Objects with low structural integrity, loose aggregations of debris held together by weak gravitational attraction, respond dramatically to such tidal stresses, sometimes fragmenting completely when tidal forces exceed the nucleus's self-gravity. But 3I-ATLAS maintains structural coherence despite experiencing tidal accelerations that would disrupt many small solar system bodies. This resilience suggests either unusually strong internal cohesion, perhaps resulting from sintering processes during its long journey through interstellar space, or a nucleus composition dominated by relatively large, structurally sound fragments rather than loose collections of dust and ice. The comet's ability to survive tidal encounters provides constraints on its internal density and mechanical properties that complement spectroscopic observations of surface composition. The orbital calculations also reveal subtle non-gravitational accelerations caused by asymmetric outgassing from the comet's nucleus. When volatile materials sublime preferentially from one hemisphere, the resulting jet of gas and dust creates a weak rocket effect that gradually alters the trajectory in ways not predicted by gravitational forces alone. These non-gravitational accelerations prove extremely difficult to detect, requiring positional measurements accurate to arc seconds and careful modelling of all gravitational influences before the residual rocket effects become apparent. For 3I-ATLAS, the non-gravitational accelerations appear larger than typical for solar system comets of similar size and activity level. This enhanced rocket effect might result from the comet's unusual composition, with its abundance of carbon monoxide ice creating more efficient momentum transfer than the water-dominated outgassing of familiar objects. Alternatively, the comet's internal structure might allow gas jets to achieve higher velocities through nozzle effects created by subsurface cavities and fracture networks. The trajectory analysis extends beyond simple position and velocity calculations to encompass the comet's rotation state and orientation in space. Most small bodies exhibit complex rotational motion resulting from irregular shapes and internal mass distributions. Gravitational torques from the Sun and planets, combined with torques from asymmetric outgassing, can alter rotation periods and spin axis orientations over timescales ranging from days to years. Photometric observations reveal that 3I-ATLAS displays brightness variations with periodicities suggesting rotation, but the signals prove too irregular for precise period determination. This irregularity might result from chaotic tumbling motion rather than stable rotation around a principal axis, a condition that could arise from internal structural changes caused by sublimation of supporting ice deposits. Alternatively, the comet might possess a highly elongated or angular shape that creates complex light curves as different surface features rotate into and out of sunlight. The mathematical models that describe 3I-ATLAS's motion incorporate relativistic corrections for the curvature of space-time around massive objects. While these effects remain small compared to classical gravitational forces, they become measurable for objects that pass close to the Sun or experience high accelerations during planetary encounters. The inclusion of relativistic terms demonstrates the precision achievable with modern astronomical techniques, capable of detecting phenomena predicted by Einstein's theory of general relativity in the motion of a comet measuring less than a kilometre across. Long-term orbital projections reveal that 3I-ATLAS will depart our solar system along a trajectory significantly different from its approach path, having exchanged momentum and energy with our Sun through gravitational interactions. The departing hyperbola opens toward the constellation Telescopium in the southern sky, carrying the comet toward regions of space that human telescopes may never again be able to observe it. The gravitational encounter will have accelerated the comet slightly, adding energy that increases its velocity relative to nearby stars. This velocity increase means that 3I-ATLAS will traverse the galaxy faster during the remainder of its existence than it did during the journey to our solar system. The comet's next stellar encounter might occur sooner than the millions of years typically required for interstellar travel, though predicting such interactions requires knowledge of stellar motions and galactic dynamics that exceed current observational capabilities. The mathematics of orbital mechanics provide precise short-term predictions, but dissolve into statistical uncertainties when extended across galactic timescales. The orbital analysis of 3I-ATLAS thus represents both a triumph of celestial mechanics and a reminder of the universe's vast scales. Human mathematics can describe the comet's motion through our solar system with extraordinary precision, predicting its position months or years in advance to accuracies measured in kilometres. Yet that same precision evaporates when extended to galactic scales, where chaotic interactions with countless stars render long-term predictions impossible. The comet exists simultaneously as a perfectly predictable mechanical system and as a chaotic wanderer whose ultimate fate remains forever unknowable. Deep within the nuclear ice of 3I-ATLAS, molecular structures preserve information about temperatures, pressures, and chemical environments that existed during the comet's formation billions of years ago. Each ice crystal contains within its lattice arrangement a record of the conditions under which water, carbon and monoxide, and other volatiles condensed from vapour into solid form. These crystalline archives differ fundamentally from the ice structures familiar on Earth, having formed not in our planet's moderate climate but in the extreme cold and near-vacuum conditions surrounding an alien star. Water ice can exist in more than a dozen distinct crystalline forms, each stable under different combinations of temperature and pressure. On Earth, we encounter primarily hexagonal ice, the familiar structure that creates snowflakes and fills our freezers with its regular six-sided symmetry. But in the deep cold of interstellar space, water molecules arrange themselves into amorphous ice, a glassy structure lacking the ordered crystalline geometry that characterizes terrestrial frozen water. This amorphous form possesses different density, thermal properties, and sublimation characteristics than familiar hexagonal ice. The transformation between these ice phases occurs through processes that operate over geological timescales in space environments. Cosmic radiation gradually converts amorphous ice into crystalline forms through mechanisms that remain poorly understood. Temperature fluctuations during passages near different stars can trigger phase transitions that alter the internal structure of cometary nuclei. The specific ice phases present within 3I-ATLAS encode information about its thermal history during millions of years of interstellar travel. Spectroscopic observations suggest that the comet contains ice structures unlike those typically found in solar system objects. The sublimation temperatures and rates observed as 3I-ATLAS approaches the Sun indicate unusual crystalline arrangements that require different energy inputs to convert from solid to vapour phases. These exotic ice structures might reflect formation conditions in the vicinity of a different type of star, perhaps a cooler red dwarf where water ice could achieve more perfect crystalline order, or a more massive blue giant where radiation fields created unusual photochemical processing of frozen materials. The carbon monoxide ice within the nucleus presents even more intriguing possibilities. This molecule forms cubic crystals at low temperatures, creating structures with mechanical properties quite different from water ice. Carbon monoxide ice possesses lower density and tensile strength than water ice, making it more susceptible to fracturing under thermal stress or tidal forces. A nucleus containing substantial quantities of carbon monoxide ice might exhibit internal fracture networks that create complex pathways for gas escape during solar heating. These internal fractures could explain the irregular outgassing behavior observed as 3IATLAS develops its Comet and tails. Solar heating penetrates only millimeters into the surface of most comets, but fracture networks could allow thermal energy to reach deeper ice deposits through convective gas flow. Subliming carbon monoxide in subsurface cavities could create gas pressure sufficient to drive further fracturing, creating a positive feedback process that accelerates the development of internal void spaces. The mechanical properties of interstellar ice also differ from terrestrial analogies due to radiation damage accumulated during the long journey between stars. Cosmic rays, high-energy particles accelerated by supernova explosions, and other violent astrophysical processes gradually alter the molecular structure of exposed ice surfaces. Each cosmic ray impact breaks chemical bonds and creates reactive fragments that can recombine into more complex organic molecules or alter the crystalline structure of surrounding ice. This radiation processing creates a weathered surface layer unlike anything found on Earth. The altered ice possesses different optical properties, sublimation characteristics, and mechanical strength than pristine interior materials. Some cosmic ray impacts create microscopic tracks, damage trails extending several micrometers into the ice, where high-energy particles disrupted the molecular lattice. These tracks serve as fossil records of radiation exposure, potentially allowing researchers to estimate how long 3IATLAS travelled through interstellar space before arriving at our solar system. Laboratory experiments attempting to replicate interstellar ice conditions reveal additional complexity in the comet's probable internal structure. When scientists create carbon monoxide and water ice mixtures under conditions simulating space environments, they find that the two materials don't form simple mechanical mixtures, but instead create complex clathrate structures, cage-like arrangements where water molecules trap carbon monoxide molecules in crystalline prisons. These clathrates possess unusual stability properties, remaining solid at temperatures where pure carbon monoxide ice would sublime rapidly. If 3IATLAS contains significant quantities of clathrate ices, its outgassing behavior would differ dramatically from models assuming simple mechanical mixtures of different ice phases. Clathrates release their trapped gases suddenly when heated beyond critical temperatures, creating the episodic brightening events that characterize the comet's observed behavior. The formation and destruction of these cage structures could explain the rapid variations in gas production rates that puzzle observers attempting to model the comet's activity. The isotopic composition of the ice provides additional constraints on formation conditions and subsequent processing. Different stellar environments produce characteristic isotopic signatures that persist for billions of years after the original nuclear reactions cease. Heavy water containing deuterium instead of normal hydrogen forms in greater abundance around certain types of stars or in molecular clouds with specific thermal histories. The deuterium to hydrogen ratio in 3IATLAS's water ice could reveal whether it formed in a stellar environment similar to our own or under dramatically different conditions. Nitrogen isotopes offer similar insights into the comet's birth environment. The nitrogen-15 to nitrogen-14 ratio varies significantly among different stellar populations, reflecting the nuclear processing history of the gas clouds from which stars and planets form. Preliminary observations suggest that 3IATLAS contains nitrogen isotopic ratios unlike those found in solar system materials, confirming its formation in an alien stellar environment with different nucleosynthetic history than our own. These isotopic measurements require extraordinary precision, as the differences between samples from different stellar environments typically amount to only parts per thousand or smaller. Ground-based spectrometers pushed to their theoretical limits can detect such variations only under optimal observing conditions, when the comet's brightness and atmospheric transparency combine to provide sufficient signal strength. Each successful measurement represents a triumph of instrumental technique and observational skill. The comparison between 3IATLAS's ice composition and that of familiar solar system comets reveals fundamental differences in planetary formation processes. Local comets formed in our Sun's protoplanetary disk, where temperatures and chemical abundances followed patterns determined by our star's mass, luminosity, and heavy element content. But 3IATLAS preserves ice that condensed under different stellar influences, creating a natural experiment in comparative planetology that extends across interstellar distances. The comet essentially provides a sample return mission from an alien stellar system, a collection of primitive materials that formed under conditions never replicated in our cosmic neighborhood. Every molecule sublimed from its surface carries information about chemical processes that operated billions of years ago in regions of space forever, beyond the reach of human spacecraft. The ice that now streams away into our solar system's vacuum once existed as vapor around a star whose light may no longer shine, preserved through the long journey between worlds like a message written in the universal language of molecular bonds. As 3IATLAS continues its approach toward the Sun, increasing thermal stress will gradually alter the ice structures that have remained stable for millions of years. Phase transitions will eliminate some crystalline arrangements while creating others. Sublimation will preferentially remove the most volatile components, changing the overall composition of the remaining nucleus. The comet that emerges from its passage through the inner solar system will possess internal structure significantly different from the pristine interstellar wanderer that first entered our gravitational domain. This transformation represents both scientific opportunity and loss, the chance to study exotic ice phases under controlled heating conditions, balanced against the irreversible destruction of information that took millions of years to preserve during the journey between stars. Each observation captures a moment in the comet's evolution from alien ice archive to dispersing cloud of molecules, documenting the gradual conversion of solid matter into the tenuous medium that fills interplanetary space. The solar wind encounters 3IATLAS like an invisible ocean meeting an unfamiliar shore, creating phenomena that illuminate both the nature of our star's extended atmosphere and the alien characteristics of the interstellar visitor. This continuous stream of charged particles, protons, and electrons, accelerated to supersonic velocities by magnetic processes in the Sun's corona, carries with it magnetic field lines that permeate the entire solar system like ghostly threads connecting our star to the most distant planetary orbits. At the comet's position, still beyond the orbit of Jupiter, the solar wind travels at approximately 400 kilometers per second, fast enough to circle Earth's equator in less than 2 minutes. These particles carry kinetic energy sufficient to ionize neutral gas molecules through direct collisions, transforming the comet's developing coma from a collection of electrically neutral atoms and molecules into a complex plasma containing ions and free electrons. This ionization process creates the brilliant gas tail that points perpetually away from the Sun, regardless of the comet's orbital motion. The interaction begins subtly as the first wisps of carbon monoxide and water vapor escape from 3IATLAS's nucleus and encounter solar ultraviolet radiation. Photons with energies exceeding 13 electron volts possess sufficient energy to strip electrons from neutral molecules, creating positive ions that respond immediately to magnetic fields embedded in the solar wind. These newly created ions find themselves swept up in the solar wind's magnetic embrace, accelerated away from the comet at velocities approaching those of the wind itself. But 3IATLAS presents the solar wind with chemical compositions unlike those encountered in typical solar system comets. The abundance of carbon monoxide creates ion populations dominated by CO+, rather than the water-derived ions that characterize most cometary plasma tails. carbon monoxide ions possess different mass-to-charge ratios than water group ions, causing them to respond differently to magnetic field configurations and creating plasma dynamics that deviate from standard theoretical models. The comet's coma also contains unusual abundances of nitrogen molecules that ionize to form N2+, ions species rarely detected in significant quantities around solar system comets. These molecular ions create spectral emission lines at wavelengths that initially confused observers accustomed to analyzing more typical plasma compositions. The unfamiliar emission spectrum required careful comparison with laboratory measurements to identify the contributing ion species and understand their formation mechanisms. As the solar wind magnetic field lines encounter the growing cloud of ions surrounding 3IATLAS, they become loaded with charge particles that alter their propagation characteristics. The magnetic field lines stretch and bend under the weight of accumulated ions, creating complex three-dimensional structures that channel plasma flow in directions determined by the geometry of magnetic field configurations. These field line distortions can be detected by spacecraft-based magnetometers located elsewhere in the solar system, providing remote sensing capabilities for studying cometary plasma interactions. The process creates a form of magnetic connection between 3IATLAS and the Sun itself, as field lines originating in the solar corona extend across millions of kilometers to embrace the comet's ionized coma. This magnetic coupling allows energy and momentum transfer between our star and the interstellar visitor, creating dynamic systems that respond to changes in solar wind conditions with time delays measured in hours rather than days or weeks. Solar wind variations driven by solar flare activity or coronal mass ejections create corresponding changes in the comet's plasma environment. When high-speed solar wind streams encounter 3IATLAS, the enhanced ion acceleration creates brighter gas tails and stronger emission lines in the comet's spectrum. When solar wind velocities decrease or magnetic field strengths weaken, the plasma tail dims accordingly, creating temporal variations that track solar activity levels across the inner solar system. These interactions provide natural laboratories for studying magneto-hydrodynamic processes under conditions impossible to replicate in terrestrial experiments. The comet's plasma environment extends across thousands of kilometers, creating spatial scales that dwarf the largest magnetic confinement devices constructed in Earth-bound laboratories. The magnetic field strengths, particle densities, and flow velocities achieved in the comet's magnetosphere represent extreme parameter regimes that test theoretical understanding of plasma physics principles. Measurements obtained by deep space missions operating elsewhere in the solar system contribute additional perspectives on the comet's plasma interactions. The Parker Solar Probe, designed to study solar wind properties near the Sun, can detect disturbances in the solar wind flow created by 3IATLAS's plasma interactions and transmitted outward along magnetic field lines. The Voyager spacecraft, now operating in the interstellar medium beyond the solar system's boundaries, provide baseline measurements of the undisturbed solar wind that help quantify the comet's influence on local space weather conditions. The comet's unusual composition creates plasma chemistry unlike anything observed in solar system objects. Carbon monoxide ions undergo charge exchange reactions with neutral hydrogen atoms in the solar wind, creating excited carbon and oxygen atoms that emit characteristic spectral lines. These emission features provide diagnostic information about both the ion densities in the comet's coma and the neutral hydrogen abundance in the local solar wind, creating opportunities for simultaneous plasma and solar wind measurements using a single target object. Nitrogen molecular ions contribute additional complexity through dissociative recombination processes that break N2+ ions into individual nitrogen atoms when they encounter free electrons. This process creates nitrogen atom emission lines that appear at specific wavelengths in the comet's spectrum, but only when electron densities exceed critical threshold values. The presence or absence of these emission lines thus provides information about the electron density distribution within the comet's plasma environment. The magnetic field interactions also create opportunities for radio wave generation through mechanisms similar to those that produce Jupiter's intense radio emissions. When plasma instabilities develop in regions where solar wind magnetic field lines intersect the comet's ionosphere, they can generate electromagnetic waves at frequencies ranging from a few kilohertz to several megahertz. These waves propagate through interplanetary space at light speed, potentially detectable by radio telescopes on Earth or by spacecraft equipped with sensitive radio receivers. The plasma tail's response to solar wind conditions creates a form of space weather monitoring system, with 3IATLAS serving as a natural solar wind probe located far from Earth's magnetosphere. Changes in tail brightness, orientation, and spectral characteristics provide real-time information about solar wind velocity, magnetic field strength, and particle density at the comet's location. This information proves particularly valuable for understanding how solar wind properties vary with distance from the Sun and how they respond to solar activity cycles. The encounter between solar wind and comet also demonstrates fundamental principles of magnetospheric physics that apply to planetary magnetospheres throughout the solar system. The formation of plasma boundaries, the acceleration of charged particles along magnetic field lines, and the generation of magnetic field disturbances around 3IATLAS follow physical laws that govern similar processes at Earth, Jupiter, and Saturn. The comet provides a simplified system for studying these processes without the complications introduced by planetary magnetic fields and atmospheric interactions. As 3IATLAS continues its journey toward the inner solar system, the solar wind intensity will increase according to the inverse square law, creating progressively more dramatic plasma interactions. The comet's gas tail will brighten and extend to greater lengths, while the plasma density and magnetic field disturbances grow more pronounced. Each stage of this evolution provides opportunities to study plasma physics under systematically varying conditions, creating a natural laboratory experiment that unfolds over months as the comet approaches our star. The solar wind encounter thus transforms 3IATLAS from a passive collection of ice and rock into an active participant in solar system plasma dynamics, demonstrating how interstellar visitors can serve as probes for investigating the space environment around our star while simultaneously revealing their own alien characteristics through their responses to local conditions. The structural integrity of 3IATLAS begins to surrender to solar forces with a slow-motion grace that unfolds across weeks and months, each passing day bringing new evidence of internal fractures spreading through the comet's nucleus like cracks appearing in ancient stone. The disintegration proceeds not through dramatic explosive events, but through the patient accumulation of thermal stresses that gradually overcome the weak gravitational and chemical bonds holding the nucleus together. What emerges from this process reveals the comet's internal architecture grain by grain, layer by layer, as if solar heating were performing a careful archaeological excavation of alien materials. The first signs appear as subtle changes in the comet's brightness patterns, irregular fluctuations that suggest non-uniform outgassing from a surface developing new fracture networks. Thermal expansion and contraction cycles create mechanical stresses within the nucleus as solar heating penetrates deeper into subsurface ice deposits. Different ice compositions expand at different rates when heated, creating internal tensions that must find release through structural failure. Carbon monoxide ice, with its lower sublimation temperature and different thermal expansion properties than water ice, creates particularly severe stress concentrations at boundaries between different compositional regions. High-resolution imaging from the Hubble Space Telescope begins to detect elongation in the comet's apparent shape, suggesting that the nucleus has developed a more pronounced non-spherical geometry as internal stresses reshape its structure. The comet appears to be slowly stretching along its rotation axis, like taffy being pulled by invisible forces. This elongation might result from rotational stresses that become significant as outgassing reduces the nucleus mass and alters its moment of inertia, or from tidal forces that become more pronounced as internal cohesion weakens. Spectroscopic monitoring reveals increasingly complex molecular emission patterns as new surface areas become exposed through fracturing processes. Previously buried ice deposits reach the surface and begin subliming, contributing molecular species to the coma that weren't present in earlier observations. The appearance of new emission lines suggests that the comet's nucleus possesses a layered internal structure, with different ice compositions stratified according to their condensation temperatures during the original formation process billions of years ago. The fragmentation process creates observational opportunities unavailable for structurally intact comets. As pieces of the nucleus separate and develop independent trajectories, astronomers can study materials from different depths within the original body. Each fragment carries with it samples from specific internal regions, providing natural core samples that reveal the comet's compositional stratigraphy. The fragments also develop their own individual comas as exposed ice begins subliming, creating multiple sources of gas and dust that can be analysed separately. Photometric observations detect the emergence of distinct brightness peaks in the comet's light curve, suggesting that several large fragments now orbit around a common centre of mass. These fragments appear to maintain gravitational contact despite their structural separation, creating a loose aggregate system held together by mutual attraction between components too massive to escape each other's weak gravitational influence. The resulting orbital mechanics create complex rotational patterns as individual pieces tumble while orbiting their shared barycenter. The dust production rate increases dramatically as new surface areas become exposed through the fragmentation process. Fresh ice surfaces sublime more efficiently than weathered exterior layers that have been altered by cosmic radiation exposure, creating enhanced outgassing that brightens the comet's dust tail significantly. The increased dust production also reveals information about grain size distributions and mineral compositions that were previously hidden beneath protective surface layers. Analysis of the dust size distribution shows that 3IATLAS produces particles with characteristics different from typical solar system comets. The fragments contain higher proportions of large grains, particles measuring hundreds of micrometers across rather than the predominantly smaller dust typical of local comets. This grain size distribution suggests that the comet's internal structure consists of relatively large solid particles bound together by ice matrices, rather than the fine-grained aggregates that characterize many solar system comet nuclei. The larger grain sizes also affect the dynamics of dust tail formation, as more massive particles respond less readily to solar radiation pressure. The result creates a dust tail with unusual morphology, a broad, diffuse structure that doesn't follow the narrow, well-defined arc typical of comets, dominated by small dust particles. The tail's appearance provides additional evidence of the comet's alien origin and internal structure. Thermal modelling of the fragmentation process suggests that internal temperature gradients create the stresses responsible for structural failure. Solar heating creates a warm surface layer while deeper regions remain at temperatures near absolute zero, establishing thermal gradients steep enough to generate significant mechanical stresses. These stresses accumulate over multiple rotation periods as different parts of the nucleus experience varying solar illumination, eventually exceeding the tensile strength of weakened materials. The exotic ice compositions within 3IATLAS contribute to accelerated fragmentation through several mechanisms. Carbon monoxide ice undergoes phase transitions at temperatures different from water ice, creating volume changes that generate internal pressure. Clathrate hydrates, cage-like structures where water molecules trap other gas molecules, can destabilize suddenly when heated beyond critical temperatures, releasing trapped gases in ways that create internal explosions. These processes operate more efficiently in the comet's alien ice mixture than in the water-dominated compositions of solar system comets. Radio observations detect bursts of emission at frequencies characteristic of electrical discharge processes, suggesting that fragmentation events create electrostatic effects as charged dust particles separate from the nucleus. The breakup of ice structures can generate static electricity through triboelectric processes, the same mechanism that creates lightning in terrestrial thunderstorms. These electrical discharges might contribute to the acceleration of charged dust particles and the creation of plasma instabilities within the comet's coma. The fragmentation also reveals information about the comet's original formation environment. The weak internal cohesion that allows easy structural failure suggests formation through gentle accretion processes rather than violent collisional assembly. The comet likely accumulated from small particles that stuck together through van der Waals forces and ice sintering, creating a structure more like compressed snow than welded rock. This formation mechanism implies birth in a quiescent region of its stellar system, perhaps in the outer regions where gravitational perturbations remained minimal. Each fragment that separates from the main nucleus carries with it information about specific internal regions and formation processes. Some fragments appear dominated by carbon monoxide ice, creating brilliant gas tails with distinctive spectral characteristics. Others contain higher proportions of water ice and dust, producing behavior more similar to familiar solar system comets. This compositional diversity within a single object demonstrates the complex accretion history that created 3IATLAS in its alien birth environment. The ongoing disintegration creates a race against time for observers attempting to characterize the comet before it completely disperses. Each week brings new structural changes that alter the comet's behavior and appearance. What began as a single nucleus develops into a complex system of fragments, dust clouds, and gas streams that challenges traditional concepts of what constitutes a comet. The transformation demonstrates the dynamic nature of small solar system bodies and the powerful forces that solar heating can exert on objects formed under different conditions. As the fragmentation continues, 3IATLAS evolves from a preserved sample of alien materials into a dispersed cloud of molecules and particles that will eventually merge with the interplanetary medium. The comet's structural failure represents both the loss of a unique scientific target and the creation of new opportunities to study exotic materials under conditions impossible to achieve through any other means. Each crumbling piece carries with it fragments of information about stellar formation processes that operated billions of years ago in distant regions of the galaxy. Observatory domes across Earth's continents open to the night sky with mechanical precision, their massive telescopes swiveling toward the constellation where 3IATLAS continues its slow dissolution against the stellar background. Time becomes the enemy now, each passing night bringing the interstellar visitor closer to complete disintegration, while simultaneously making it more accessible to detailed observation. The global astronomical community mobilizes with the efficiency born of understanding that some celestial phenomena offer only brief windows for study, after which their secrets vanish forever into the cosmic void. The Atacama Large Millimeter Array high in Chile's desert coordinates its 66 radio dishes to create a synthetic aperture spanning 16 kilometers, focusing on molecular emission lines that reveal the chemical composition of gas streaming from the fragmenting nucleus. Each antenna operates with clockwork precision, their signals combined through sophisticated interferometry techniques that achieve angular resolution impossible with single telescopes. The resulting observations detect carbon monoxide, formaldehyde, methanol, and hydrogen cyanide in abundances that confirm the comet's exotic chemistry, while raising new questions about formation processes in alien stellar systems. Simultaneously, the Very Large Telescope's 4 8-meter mirrors work in unison to obtain high-resolution spectra that dissect the comet's light into its component wavelengths with unprecedented detail. These observations reveal isotopic ratios that differ subtly but measurably from solar system norms carbon-13 to carbon-12 ratios that suggest nucleosynthesis in a stellar environment with different mass and metallicity than our Sun. Each measurement requires hours of exposure time to achieve the signal-to-noise ratios necessary for reliable isotopic analysis, creating observational campaigns that extend across multiple nights as the comet slowly brightens and fragments. Space-based telescopes contribute capabilities impossible from Earth's surface, where atmospheric absorption blocks access to crucial wavelength regions. The Hubble Space Telescope provides ultraviolet spectroscopy that reveals the ionization state of gases in the comet's coma, while infrared space observatories measure thermal emission from dust particles heated by solar radiation. These complementary observations create a comprehensive picture of physical and chemical processes operating as the interstellar visitor responds to our Sun's influence. The James Webb Space Telescope, with its unprecedented sensitivity in the infrared, detects molecular species previously unobservable in cometary spectra. Complex organic molecules methane, ethane, acetylene appear in emission lines so faint that earlier instruments could never have detected them. These observations suggest that 3IATLAS contains organic chemistry created through processes operating in its birth stellar system, preserved through millions of years of interstellar travel like molecular fossils from an alien world. Amateur astronomers contribute observations that complement professional data through their ability to monitor the comet continuously across multiple longitude zones. A network of dedicated observers equipped with CCD cameras and modest telescopes creates a global surveillance system that tracks brightness variations on timescales of hours rather than days. These rapid monitoring capabilities prove crucial for understanding the episodic fragmentation events that occur as internal stresses overcome the nucleus's weakening structural integrity. The coordination between professional and amateur observers demonstrates astronomy's collaborative nature, where discoveries emerge through the combination of expensive space-based instruments and patient ground-based monitoring by enthusiasts who understand the value of systematic observation. Electronic networks allow real-time sharing of data, creating a global brain that processes information about 3IATLAS's behavior faster than any single observatory could achieve working in isolation. Theoretical modeling teams work around the clock to interpret the flood of observational data, creating computer simulations that attempt to reproduce the comet's unusual outgassing patterns and fragmentation behavior. These models incorporate exotic ice physics, plasma interactions, and thermal stress calculations that push computational capabilities to their limits. Each successful model prediction validates theoretical understanding, while each failure reveals gaps in knowledge about processes operating under conditions that never occur in our solar system. The modelling efforts reveal fundamental challenges in understanding objects formed under alien stellar conditions. Standard comet models assume water ice dominance and thermal properties derived from solar system materials, but 3IATLAS defies these assumptions at every turn. Its carbon monoxide-rich composition requires modifications to sublimation physics, while its unusual structural weakness demands new approaches to calculating thermal stress distributions and fragmentation thresholds. Spectrometers around the world focus on detecting increasingly rare molecular species as the comet's chemistry becomes more accessible through ongoing fragmentation. Deuterated molecules containing heavy hydrogen atoms appear in trace quantities that provide information about temperature conditions during the comet's formation. The deuterium to hydrogen ratio differs significantly from solar system values, suggesting formation in a molecular cloud with different thermal history than the nebula that created our planetary system. Radio telescopes contribute observations of molecular masses, natural amplification of specific emission lines that occur when physical conditions create population inversions in molecular energy levels. These Mahler emissions, detected primarily in methanol and water molecules, provide information about gas densities and temperatures in regions of the comet's coma where other techniques fail. The Massa observations also reveal rapid time variations that suggest turbulent gas dynamics, as fragmentation events create shock waves propagating through the coma. X-ray observatories detect unexpected emissions from the comet's plasma environment, where solar-wind interactions create conditions conducive to charge exchange processes between highly ionized solar wind ions and neutral molecules in the coma. These X-ray emissions provide remote sensing capabilities for measuring solar wind properties at the comet's location, turning 3IATLAS into a natural space weather monitoring station positioned far from Earth's magnetospheric interference. The observational campaign faces increasing urgency as thermal modelling predicts complete structural collapse within months rather than years. Each new fragmentation event reduces the comet's mass and alters its outgassing patterns, creating a moving target that challenges observers attempting to plan systematic measurement programs. The comet's behavior becomes increasingly erratic as structural integrity fails, making prediction of future observing conditions nearly impossible. Data archival systems struggle to accommodate the volume of information generated by the global observational campaign. Terabytes of spectra, images, and photometric measurements flow into databases that must be processed, calibrated, and made available to the worldwide research community. The data management challenges rival those faced during major space missions, requiring unprecedented coordination between observatories and data centers. Some observers focus on capturing the comet's current state with exhaustive completeness, understanding that future researchers may need access to measurements that seem insignificant now, but could prove crucial for understanding processes not yet recognized. Others prioritize specific observations designed to test particular theoretical predictions about exotic ice behavior or plasma physics under unusual conditions. The diversity of observational strategies reflects the community's recognition that 3IATLAS represents a unique opportunity unlikely to be repeated during current careers. The psychological pressure on observers intensifies as the comet continues its gradual dissolution. Each clear night becomes precious. Each instrument failure or weather delay represents irreplaceable lost opportunities. The global astronomy community experiences a collective awareness that they are witnessing phenomena that may not occur again for decades, creating an atmosphere of scientific urgency that transcends normal research timelines and competitive boundaries. As 3IATLAS approaches its closest point to the Sun, the rate of change accelerates beyond the ability of systematic observation programs to track. The comet transforms from week to week, sometimes from night to night, as solar heating drives fragmentation processes to completion. What began as a systematic study of an unusual interstellar visitor evolves into a frantic effort to document a cosmic catastrophe in real time, recording the death throes of an object that carried information across the galaxy for millions of years, only to surrender its secrets during a few brief months of visibility from Earth. In conference rooms scattered across multiple continents, theoretical astrophysicists gather around whiteboards covered with equations describing stellar nucleosynthesis, protoplanetary disk chemistry, and the gravitational dynamics of planetary system formation. The unusual properties of 3IATLAS have sparked intensive modelling efforts aimed at identifying which stellar environments could produce objects with such exotic compositions and behaviours. Each proposed formation scenario must explain not only the comet's carbon monoxide-dominated ice chemistry, but also its structural weakness, isotopic signatures, and survival during millions of years of interstellar travel. The first theoretical framework considers formation in the debris disk surrounding a dying red giant star, where temperatures and chemical abundances differ dramatically from those that characterized our Sun's protoplanetary nebula. Red giant stars expand to enormous sizes during their final evolutionary phases, creating circumstellar environments where carbon-bearing molecules achieve concentrations impossible around main-sequence stars. These expanded stellar atmospheres lose mass continuously through stellar winds that carry carbon monoxide, methane, and other reduced compounds into surrounding space, where they can condense into ice particles under appropriate conditions. Computer simulations of red giant mass loss reveal temperature profiles that would favour carbon monoxide ice condensation at distances comparable to our solar system's outer planet regions. Unlike our Sun's protoplanetary disk, where water ice dominated the solid phase chemistry beyond the snow line, a red giant's debris disk might contain regions where carbon monoxide ice forms as readily as water ice formed during our system's birth. These conditions could produce comet nuclei with the carbon monoxide abundances observed in 3IATLAS, explaining its premature outgassing and unusual spectral characteristics. Alternative formation scenarios focus on stellar nurseries within giant molecular clouds, where supernova explosions and massive star winds create chemical environments enriched in carbon and nitrogen compounds. These regions experience shockwave compression that triggers rapid cooling and condensation of gas phase molecules into solid particles. The shock processing can create unusual isotopic ratios through nuclear reactions that operate during the brief periods of extreme temperature and pressure. Objects forming in such environments might preserve isotopic signatures different from those typical of more quiescent star formation regions. Theoretical models of molecular cloud chemistry predict that certain cloud regions could achieve carbon monoxide to water ratios approaching those observed in 3IATLAS. These calculations incorporate complex networks of gas phase and grain surface chemical reactions that operate over millions of years as molecular clouds evolve toward gravitational collapse and star formation. The models suggest that chemical gradients within large molecular clouds could create zones where carbon-bearing ices dominate over oxygen-bearing species. Contrary to the water-dominated chemistry that characterized our solar system's formation region, the comet's unusual structural weakness poses additional constraints on formation scenarios. Most theoretical models predict that objects forming in gravitationally bound systems should achieve reasonable structural integrity through sintering processes that weld ice particles together over geological timescales. But 3IATLAS appears to possess internal cohesion barely sufficient to maintain structural unity, suggesting formation through gentle accretion processes that avoided the compaction and heating associated with more violent assembly mechanisms. One possibility involves formation in the outer regions of a protoplanetary disk, where gravitational perturbations remained minimal and collision velocities stayed below the threshold for significant compaction. Such environments might exist around low-mass stars where disk temperatures never rose high enough to drive extensive thermal processing of solid materials. Objects forming under these conditions could retain the fluffy, weakly bound structures observed in some solar system comets. But with chemical compositions determined by the different stellar environment, alternative scenarios propose formation through direct condensation from gas phase materials in interstellar space, bypassing traditional protoplanetary disk processes entirely. Certain regions of molecular clouds experience conditions where gas densities and cooling rates permit direct ice grain formation, without requiring solid surfaces for condensation nucleation. These interstellar snowflakes could achieve the chemical compositions observed in 3IATLAS, while maintaining the weak structural integrity that makes them susceptible to fragmentation under minimal stress. The isotopic ratios measured in 3IATLAS provide crucial tests of formation theories, as different stellar environments produce characteristic nuclear signatures that persist for billions of years. Carbon-13 to carbon-12 ratios reflect the nuclear burning processes that operated in whatever stars contributed material to the comet's birth region. Nitrogen isotope ratios carry information about supernova nucleosynthesis and chemical evolution processes that operated in the galactic environment where the comet formed. Preliminary isotopic measurements suggest 3IATLAS formed in a stellar environment with metallicity, the abundance of elements heavier than hydrogen and helium, different from our Sun's neighborhood. These metallicity differences could arise from formation in a different galactic location, perhaps closer to the galactic center, where stellar populations possess different chemical abundance patterns. Alternatively, the comet might originate from an earlier epoch of galactic evolution, when supernova enrichment had created different background abundances of heavy elements. Stellar evolution calculations provide additional constraints on possible formation environments by predicting which types of stars could create circumstellar conditions suitable for carbon monoxide-rich comet formation. Asymptotic giant branch stars evolved objects experiencing thermal pulsing that dredges carbon from interior nuclear burning regions to surface layers represent prime candidates for creating carbon-enriched debris disks. These stars lose substantial mass through stellar winds that could transport carbon-bearing molecules to distances where ice condensation becomes possible. Wolf-Rayet stars present another possibility, as these massive objects experience extreme mass loss rates that create circumstellar environments dominated by carbon and nitrogen compounds. The stellar winds from Wolf-Rayet stars achieve velocities sufficient to transport material across interstellar distances. potentially seeding molecular clouds with exotic chemical compositions that could influence subsequent generations of star and comet formation. The theoretical challenges multiply when considering how objects like 3IATLAS could survive ejection from their birth systems and subsequent interstellar travel. Gravitational encounters with planets or other massive objects typically impart high velocities that should disrupt weakly bound structures through tidal forces or high-speed collisions with interstellar debris. The comet's survival suggests either unusual structural properties that enhance resistance to disruption or ejection mechanisms that minimize destructive processes during escape from the birth system. Recent theoretical work on planetary system dynamics identifies several mechanisms that could eject comet-like objects while preserving their structural integrity. Gravitational resonances with migrating giant planets could gradually increase orbital eccentricities until objects achieve escape velocity without experiencing violent encounters. Stellar flybys could perturb outer system objects into hyperbolic trajectories through gentle gravitational torques rather than direct impacts or close approaches. The comet's current trajectory provides additional constraints on ejection mechanisms and subsequent galactic motion. Its approach velocity and direction suggest origin from a stellar system located within a few hundred light-years of our current position, implying either recent ejection from a nearby system or formation in a stellar cluster that has since dispersed through galactic rotation. These geometric constraints limit the range of possible formation scenarios and provide targets for future observations aimed at identifying the comet's birth system. Theoretical modelling teams continue refining their calculations as new observational data becomes available, creating an iterative process where observations guide theory development, while theoretical predictions identify crucial measurements needed to distinguish between competing formation scenarios. The unusual properties of 3IATLAS have stimulated advances in understanding stellar nucleosynthesis, protoplanetary disk chemistry, and the ejection dynamics that populate interstellar space with small bodies, carrying information about diverse stellar environments across the galaxy. The observational record of 3IATLAS grows thicker with each passing week, accumulating in digital archives where terabytes of spectra, photometry, and high-resolution imagery preserve the systematic documentation of the comet's gradual transformation from solid nucleus to dispersed cloud of molecules. These datasets represent far more than simple astronomical observations. They constitute a comprehensive library of measurements that capture the behavior of interstellar material under controlled heating conditions, creating a scientific legacy that will inform research for decades after the comet itself has completely dissolved into the interplanetary medium. Professional observatories contribute observations with technical specifications that push instrumental capabilities to their theoretical limits. The Keck Observatory's 10-meter mirrors achieve spectral resolutions approaching 100,000, sufficient to detect isotopic ratios through minute shifts in molecular emission line wavelengths. These measurements require exposure times extending across entire nights, during which the telescope tracks the comet's motion with precision measured in arc-seconds, while atmospheric turbulence and instrumental variations threaten to compromise data quality. Each successful observation represents a triumph of technical expertise and persistence, as the comet's fragmenting nucleus creates an increasingly challenging target for systematic study. Brightness variations occur unpredictably as new fractures expose fresh ice surfaces, or structural collapses alter the geometry of gas jets emerging from the nucleus. Observers must adapt their measurement strategies continuously, balancing the desire for systematic monitoring against the need to capture unexpected phenomena as they occur. Space-based observatories provide measurements impossible from Earth's surface, where atmospheric absorption blocks access to crucial wavelength regions that contain diagnostic information about the comet's exotic chemistry. The Hubble Space Telescope's ultraviolet spectrometers reveal ionization processes occurring in the comet's coma as solar radiation strips electrons from neutral molecules, creating plasma populations with characteristics that reflect the unusual molecular abundances present in the nucleus. These UV observations complement visible light measurements, creating a comprehensive picture of physical processes operating across different energy regimes. Infrared space telescopes contribute thermal measurements that constrain the physical properties of dust particles streaming from the fragmenting nucleus. These particles carry direct samples of solid materials formed in the comet's birth stellar system, preserved through millions of years of interstellar travel like microscopic time capsules from an alien world. The thermal infrared observations reveal particle-size distributions, mineral compositions, and crystalline structures that provide insights into condensation processes that operated under stellar conditions different from those that created our solar system. Radio telescopes detect molecular emission lines at frequencies blocked by Earth's ionosphere, revealing the presence of complex organic compounds that form through photochemical reactions as simple molecules released from the nucleus encounter solar ultraviolet radiation. These radio observations require sophisticated interference mitigation techniques to separate astronomical signals from terrestrial radio frequency pollution, creating technical challenges that demand coordination between multiple observatories to achieve reliable detections of weak molecular emissions. The accumulating observations reveal temporal patterns that illuminate the internal structure and composition of the comet's nucleus. Periodic variations in outgassing rates suggest rotational modulation as different surface compositions rotate into and out of solar illumination. But the periods prove irregular, changing over timescales of days as structural modifications alter the nucleus shape and mass distribution. These changes create a moving target that challenges attempts to establish systematic monitoring programs. Amateur astronomers contribute crucial observations through their ability to monitor the comet continuously across multiple time zones and weather patterns. Networks of dedicated observers equipped with CCD cameras and computer-controlled telescopes provide photometric measurements with temporal resolution impossible to achieve with major observatories that must divide their time among multiple research programs. These amateur observations often capture transient phenomena, sudden brightness changes, new jet formations, fragmentation events that occur between scheduled professional observations. The collaboration between professional and amateur astronomers demonstrates the democratized nature of modern observational astronomy, where electronic networks allow real-time sharing of data and coordination of observational campaigns. Social media platforms designed for astronomical research enable rapid communication of new discoveries and coordination of follow-up observations, creating a global brain that processes information about 3IATLAS faster than traditional publication mechanisms could achieve. Photometric monitoring reveals brightness variations that follow no predictable pattern, suggesting chaotic tumbling motion rather than stable rotation around a principal axis. This rotational chaos might result from internal mass redistribution as volatile materials sublime preferentially from certain regions, altering the nucleus moment of inertia and destabilizing rotational motion. Alternatively, asymmetric outgassing could create torque sufficient to overcome rotational inertia, forcing the nucleus into complex tumbling states that defy simple periodic analysis. High-resolution imaging from the largest ground-based telescopes begins to resolve the comet's nucleus as an extended object rather than a point source, revealing elongation that increases over time as tidal forces and internal stresses stretch the weakly bound structure. These morphological changes occur slowly enough to be tracked across multiple observing seasons, creating time-lapse documentation of structural failure in an interstellar object subjected to solar heating. The imaging observations also detect the formation of multiple brightness peaks within the comet's apparent profile, suggesting fragmentation into several distinct pieces that maintain gravitational association while developing independent trajectories. Each fragment creates its own coma as newly exposed ice surfaces begin subliming, creating a complex system where multiple sources contribute gas and dust to the overall brightness pattern. Spectroscopic monitoring tracks the evolution of molecular emission lines as fragmentation exposes different internal layers with varying compositions. The appearance of new molecular species in the spectrum indicates that the nucleus possesses internal structure with compositional gradients that reflect formation or processing history. Water vapor emissions strengthen as fragmentation exposes water-rich interior regions previously shielded by carbon monoxide-dominated surface layers. These spectral changes provide natural core samples from different depths within the original nucleus, revealing information about accretion processes and chemical gradients that developed during formation in the comet's birth stellar system. The temporal sequence of molecular appearances creates a stratigraphic record that can be interpreted like geological layers in terrestrial rock formations, with each newly exposed composition representing a different epoch or environment during the comet's formation history. Isotopic measurements push analytical techniques to their precision limits, requiring signal-to-noise ratios achievable only through very long exposures using the most sensitive instruments available. The detection of deuterated molecule species containing heavy hydrogen provides information about temperature conditions during ice formation, as deuterium fractionation processes operate differently under various thermal regimes. These measurements suggest formation temperatures significantly different from those that characterized our solar system's comet-forming regions. Polarization measurements reveal properties of dust particles that cannot be determined through other techniques. The degree and orientation of polarization depend on particle shape, size distribution, and composition, providing constraints on the microscopic properties of solid materials liberated from the nucleus. These measurements suggest that 3I-ATLAS produces dust particles with characteristics different from typical solar system comets, possibly reflecting different mineral compositions or grain aggregation processes that operated in its alien birth environment. The growing database of observations creates opportunities for statistical analysis and pattern recognition that might reveal subtle phenomena invisible in individual measurements. Machine learning algorithms trained on the accumulated datasets begin identifying correlations between different observational parameters, suggesting physical relationships that human analysts might not recognize through traditional data analysis techniques. These computational approaches represent new frontiers in astronomical data analysis, where artificial intelligence techniques help extract maximum scientific information from complex, multi-dimensional datasets. Each observation adds another piece to the puzzle of 3I-ATLAS's nature and origin, but the complete picture remains tantalizingly incomplete as the comet continues its dissolution. The observational legacy being created will provide material for analysis long after the comet itself has vanished, ensuring that this unique interstellar visitor contributes to scientific understanding for years beyond its brief passage through our solar system. As winter deepens across Earth's northern hemisphere, 3I-ATLAS presents astronomers with increasingly puzzling behaviors that challenge every theoretical framework developed to explain cometary physics. The fragmented nucleus, now separated into multiple components orbiting their shared center of mass, displays outgassing patterns that defy conventional understanding of how ice sublimation responds to solar heating. Some fragments brighten dramatically when geometric considerations predict they should dim, while others remain stubbornly inactive despite optimal solar illumination angles. The puzzle deepens when researchers attempt to correlate outgassing activity with the comet's rotational state and internal structure. Traditional comet models assume that sublimation rates follow predictable thermal laws, with activity levels determined primarily by solar flux, surface composition, and subsurface thermal conduction. But 3I-ATLAS operates according to different rules, as if its alien ice compositions and exotic formation history have endowed it with properties that don't conform to terrestrial analogies or solar system experience. Spectroscopic observations reveal molecular emission lines that appear and disappear on timescales ranging from hours to days, suggesting dynamic processes within the fragmenting nucleus that operate much faster than simple thermal equilibration can explain. Sometimes carbon monoxide emissions dominate the spectrum so completely that other molecular species become undetectable, as if massive releases of trapped CO create temporary atmospheric conditions that suppress other chemical processes. Other times the emissions fade to barely perceptible levels, implying either cessation of outgassing or fundamental changes in the physical processes governing molecular excitation. These rapid spectral variations hint at internal mechanisms that remain poorly understood even after months of intensive observation. Perhaps subsurface cavities created by preferential sublimation of volatile ices periodically collapse, releasing trapped gases in sudden bursts that create the observed episodic brightening events. Perhaps electromagnetic effects associated with plasma interactions in the comet's ionized coma influence molecular emission through processes that don't operate in the neutral gas environments typical of most cometary observations. The comet's response to solar wind variations provides additional evidence of unusual physical processes operating within its plasma environment. When high-speed solar wind streams encounter 3IATLAS, the expected brightening of the gas tail occurs, but with intensities and spectral characteristics that exceed theoretical predictions by factors of 2 or 3. This enhanced response suggests either plasma densities much higher than estimated from other observations, or exotic plasma chemistry involving molecular species that don't exist in significant quantities around typical solar system comets. Radio telescope observations contribute another layer of mystery through the detection of molecular mesa emissions at frequencies and intensities that require physical conditions normally associated with stellar atmospheres rather than cometary comas. These mesa signals, natural amplification of specific molecular transitions, indicate regions within the comet's gas envelope where population inversions create conditions for stimulated emission. The presence of such phenomena suggests temperature and density regimes that challenge standard models of cometary atmospheres. The mesas appear intermittently, strengthening and fading according to patterns that correlate weakly with other observational parameters. Sometimes they coincide with fragmentation events, as if structural collapses create shock waves that temporarily establish the physical conditions necessary for master action. Other times they appear during periods of relative quiescence, suggesting internal processes that operate independently of the obvious structural changes occurring within the nucleus. Theoretical attempts to explain these phenomena require modifications to standard cometary physics that push models into unexplored parameter regimes. The unusual ice compositions observed in 3IATLAS with carbon monoxide abundances approaching those of water create sublimation dynamics unlike anything encountered in solar system objects. Carbon monoxide's lower sublimation temperature means that CO-rich regions become active at solar distances, where water-dominated areas remain frozen, creating internal pressure gradients that could drive complex fluid dynamics within the porous nucleus. These pressure gradients might explain the irregular outgassing patterns through mechanisms analogous to geysers or volcanic processes, where subsurface gas accumulation periodically exceeds containment pressure and erupts through surface vents. The resulting jets would carry both gas and entrained dust particles at velocities higher than typical cometary outflow speeds, creating the enhanced brightness events that punctuate the comet's otherwise steady dissolution. The electromagnetic phenomena detected around 3IATLAS present additional puzzles that resist straightforward explanation. X-ray emissions from charge exchange processes between solar wind ions and neutral molecules in the coma occur at intensities that suggest either unusually high solar wind flux or exotic molecular abundances that enhance interaction cross-sections. These X-ray observations provide remote sensing capabilities for studying solar wind properties at the comet's location, but the enhanced emission levels complicate attempts to extract quantitative measurements of solar wind parameters. Magnetic field measurements obtained by spacecraft operating elsewhere in the solar system detect perturbations that appear correlated with activity events observed at 3IATLAS, suggesting that the comet's plasma interactions create disturbances that propagate along interplanetary magnetic field lines at the solar wind's flow speed. These remote magnetic signatures provide additional evidence that the comet's plasma environment differs significantly from those created by typical solar system objects. The accumulation of anomalous observations forces researchers to confront fundamental questions about the universality of physical processes governing small body behavior. Most theoretical frameworks for cometary physics derive from observations of objects that formed in our solar system under conditions determined by our Sun's mass, luminosity, and heavy element abundance. But 3IATLAS carries the signatures of formation under alien stellar conditions, where different physical and chemical processes might have created objects with properties outside the range of local experience. This recognition leads to broader questions about the diversity of small body populations throughout the galaxy and the extent to which theoretical understanding based on solar system observations can be extrapolated to objects from different stellar environments. Each measurement of 3IATLAS's unusual behavior provides data points that will eventually inform more comprehensive theories of comet formation and evolution that encompass the full range of stellar conditions present throughout galactic history. The comet's resistance to conventional theoretical explanation also highlights the limitations of current understanding about exotic ice physics under space conditions. Laboratory simulations of interstellar ice behavior operate under approximations that may not capture the full complexity of processes occurring in actual cometary nuclei. The million-year timescales involved in interstellar travel allow subtle chemical and physical modifications that cannot be replicated in terrestrial experiments lasting days or weeks. Cosmic radiation effects present particular challenges for theoretical modelling, as the accumulated damage from high-energy particle bombardment during interstellar transit could create internal structures and chemical compositions that have no terrestrial analogues. Each cosmic ray impact creates microscopic damage tracks that could serve as preferential pathways for gas escape, altering sublimation dynamics in ways that depend on the specific radiation environment encountered during the journey between stellar systems. The unusual behavior of 3IATLAS thus serves as a natural experiment testing theoretical understanding against conditions that cannot be reproduced in laboratory settings or observed in local solar system objects. Each anomalous measurement provides insights into physical processes that operate under extreme conditions, expanding the parameter space within which astronomical theory must remain valid. The comet's refusal to conform to expectations demonstrates the universe's capacity to surprise even experienced researchers, revealing new phenomena that require extensions to existing theoretical frameworks. As the observational campaign continues, researchers begin recognizing that 3IATLAS may represent not just an unusual individual object, but potentially a member of a previously unknown class of interstellar bodies, with properties that reflect formation under stellar conditions dramatically different from those that characterized our solar system's history. This possibility transforms the scientific significance of the observations from a study of individual anomalous behavior into a glimpse of the diversity of planetary formation processes operating throughout the galaxy's stellar population. The trajectory of 3IATLAS curves inexorably outward beyond the orbit of Mars, carrying the remnants of the fragmenting comet toward the asteroid belt and eventually back into the darkness between stars. What began as a structured nucleus containing billions of years of preserved information about an alien stellar system now exists as a dispersed collection of fragments, dust clouds, and molecular gases spreading across millions of kilometers of space. The comet's passage through our solar system has transformed it from a pristine archive of interstellar chemistry into a gradually expanding nebula of exotic materials that will eventually merge with the tenuous medium filling the space between planets. Each day brings new evidence of ongoing dissolution, as solar heating continues its patient work of sublimating the remaining ice deposits and releasing dust particles that have been locked in frozen matrices since the comet's formation. The largest fragments still maintain enough structural integrity to produce detectable comas, but even these remnants shrink visibly from week to week as their surfaces retreat inward under the constant assault of solar radiation. Smaller pieces have already dispersed beyond the detection limits of most telescopes, leaving behind only the fading signatures of molecular emission lines that mark their former presence. The dust production rate has increased dramatically as fragmentation has exposed fresh ice surfaces that sublime more efficiently than the radiation-weathered exterior layers that originally protected the nucleus. This enhanced dust emission creates spectacular photographic opportunities for amateur astronomers, who capture images of flowing dust streams that stretch across degrees of sky like cosmic hair trailing behind the comet's diminishing core. The visual beauty of these displays contrasts poignantly with the knowledge that they represent the irreversible destruction of materials that survived intact for millions of years during the journey between stellar systems. Professional observations focus increasingly on rapid phenomena as the comet's behavior becomes more erratic and unpredictable. Sudden brightness changes occur without warning, as internal collapses release trapped gases or structural failures expose new ice deposits to direct solar illumination. These transient events often last only hours or days, creating observational challenges for systematic monitoring programs that must balance comprehensive coverage against the need to respond quickly to unexpected developments. The spectroscopic record reveals the gradual depletion of the most volatile components as preferential sublimation removes carbon monoxide, nitrogen, and other exotic ices faster than the water ice that forms the bulk of most cometary nuclei. This selective mass loss creates temporal changes in the comet's overall composition, with later observations showing increased water vapor emissions as the more volatile species become exhausted. The effect resembles a natural chromatography experiment, where solar heating separates different molecular species according to their sublimation temperatures. Isotopic measurements become increasingly difficult to obtain as the comet's brightness fades and molecular emission lines weaken below the detection thresholds of even the most sensitive spectrometers. The final reliable measurements of deuterium to hydrogen ratios and heavy nitrogen abundances provide closing data points for the isotopic story that began with the comet's discovery, preserving information about nucleosynthesis processes that operated in its birth stellar system billions of years before Earth existed. Radio telescope observations detect the final appearances of complex organic molecules methanol, formaldehyde, hydrogen cyanide, as photochemical reactions in the tenuous coma create these species from simpler precursors released from the sublimating nucleus. These organic emissions represent the last detectable traces of the exotic chemistry that made 3IATLAS unique among observed comets, marking the end of a molecular inventory that began under the influence of an alien star and concludes in the familiar environment of our own solar system. The plasma interactions that created the comet's distinctive gas tail continue even as the nucleus fragments dissolve, but with decreasing intensity as gas production rates fall below the levels necessary to maintain significant ionospheric densities. Solar wind magnetic field lines that once carried substantial populations of carbon monoxide and carbon dioxide ions now transport only traces of these exotic plasma components, mixed with increasing proportions of water-derived ions that characterize more typical cometary plasma tails. Gravitational analysis of the fragment trajectories reveals that most pieces lack sufficient mass to maintain mutual gravitational attraction as they spread apart under the influence of different radiation pressure forces and outgassing-induced accelerations. The comet that once existed as a coherent object held together by its own gravity now disperses according to the individual dynamics of countless separate pieces, each following slightly different orbital paths as they continue the hyperbolic trajectory that will eventually carry them out of the solar system entirely. The largest remaining fragments will likely survive passage through the inner solar system and continue outward past the orbits of the gas giant planets, gradually cooling as solar heating diminishes with increasing distance from the Sun. These survivors may preserve small quantities of exotic ice compositions for study by future missions, equipped with more advanced analytical capabilities, though their reduced size and activity levels will make them increasingly difficult targets for remote observation. Smaller fragments and individual dust particles face different fates as they encounter the complex gravitational and electromagnetic environment of the inner solar system. Some will spiral into the Sun, vaporize completely as they pass through the solar corona and contribute their exotic atomic constituents to the stellar atmosphere. Others will be deflected by gravitational encounters with planets, or scattered by radiation pressure into orbits that carry them throughout the solar system, where they may eventually impact planetary surfaces or be collected by future space missions as samples of genuine interstellar material. The molecular gases released during the comet's disintegration will persist longer than the solid fragments, spreading throughout the inner solar system as they are carried outward by the solar wind and dispersed by turbulent mixing processes. These gases will eventually become indistinguishable from the background interplanetary medium, their exotic isotopic signatures diluted below detection limits as they mix with local solar system materials. Yet they will retain their alien character indefinitely, carrying information about distant stellar nucleosynthesis processes that will circulate through our solar system for millions of years after their source has been forgotten. The observational legacy of 3IATLAS will extend far beyond the comet's physical existence, as the accumulated database of measurements provides material for theoretical analysis that may continue for decades. Each spectrum, image, and photometric data point contributes to humanity's understanding of stellar formation processes, interstellar chemistry, and the diversity of small body populations throughout the galaxy. The unusual properties that made the comet difficult to interpret during its active phase will eventually yield their secrets as theoretical frameworks evolve to encompass the broader parameter space represented by objects from different stellar environments. Future interstellar visitors may be understood more readily because of the baseline established by observations of 3IATLAS. The systematic documentation of its exotic chemistry, unusual structure, and anomalous behavior creates a reference framework for interpreting similar objects that may arrive from other stellar systems. Each new interstellar comet will be compared against the 3IATLAS standard, allowing researchers to identify which properties reflect general characteristics of interstellar objects and which represent unique signatures of specific formation environments. The scientific impact of 3IATLAS extends beyond cometary science to encompass broader questions about the chemical evolution of the galaxy and the exchange of materials between stellar systems. The comet's isotopic signatures provide direct measurements of nuclear synthesis products from stellar environments different from our own, contributing data points that constrain models of galactic chemical evolution and stellar population synthesis. These measurements represent the first direct samples of processed stellar material from beyond our solar system, opening new avenues for studying the diversity of stellar nucleosynthesis across different galactic environments. As the remnants of 3IATLAS continue their journey toward the outer solar system and eventual return to interstellar space, they carry with them subtle modifications imposed by their encounter with our Sun. Solar radiation has altered their surface compositions through photochemical processing, while gravitational interactions have changed their trajectories and rotational states. The materials that eventually escape our solar system will differ slightly from those that entered, marked by their brief passage through an alien stellar environment, just as they once carried the signatures of their birth around a different star. The darkness between stars receives back what it once released, as the dispersed fragments of 3IATLAS drift outward beyond the gravitational embrace of our solar system and return to the cosmic void from which they came. The comet's brief moment of visibility fades like a whisper across astronomical time, leaving behind only the faint traces of exotic molecules mixing slowly with the tenuous gases that fill interplanetary space. What was once a coherent messenger from alien realms becomes part of the medium through which future visitors will travel, adding its microscopic contribution to the vast inventory of materials that circulate between the stars. In the archives of observatories worldwide, digital records preserve the systematic documentation of this cosmic dissolution, thousands of spectra capturing the gradual release of molecules formed around distant suns, photometric measurements tracking the patient surrender of structure to entropy, images recording the transformation of solid matter into expanding clouds of gas and dust. These data represent humanity's first detailed study of materials that originated beyond our solar system, a scientific legacy that will inform research long after the source has vanished into galactic darkness. The questions raised by 3IATLAS settle into the slower rhythms of theoretical development, where mathematical models evolve gradually to encompass the broader universe of stellar formation processes revealed by this single visitor, Its anomalous behavior becomes reference data for understanding how different stellar environments create objects with properties outside the range of local experience. The puzzles that frustrated observers during its active phase will yield insights over decades as theoretical frameworks expand to accommodate the full diversity of planetary formation throughout the galaxy. The silence that follows is not empty but pregnant with anticipation. As radio telescopes and automated survey systems continue their patient monitoring of the sky for signs of the next interstellar wanderer. Somewhere in the darkness beyond the outer planets, other visitors may already be approaching carriers of different messages from different stellar nurseries, each bearing its own unique archive of alien chemistry and exotic physics. The universe holds countless such messengers in its vast inventory, though their arrivals remain separated by years or decades of waiting. Meanwhile, the materials that once comprised 3IATLAS continue their ancient dance through space, no longer bound by the gravity that held them together since their formation billions of years ago. Each fragment follows its own trajectory through the three-dimensional maze of gravitational fields that shapes motion on galactic scales. Some will encounter other stellar systems within a few million years, their exotic compositions perhaps seeding alien planets with isotopic signatures that preserve memories of our sun. Others will drift for hundreds of millions of years through the sparse medium between spiral arms, carrying their molecular archives through epochs that span the rise and fall of entire stellar generations. The cosmic cycles continue their patient operation, indifferent to human timescales and observational capabilities. Stars ignite and burn through their nuclear fuel, creating and distributing the heavy elements that enable complex chemistry. Molecular clouds collapse under their own gravity, forming new stellar systems where planets and comets condense from primordial nebulae. Gravitational interactions scatter some of these objects into interstellar space, beginning journeys that may last longer than the lifetimes of the stars that created them. In this endless circulation of matter and energy, the brief visibility of 3IATLAS represents merely one moment in processes that operate across billions of years. Its passage through our solar system disturbed nothing essential, while revealing everything about the universe's capacity to preserve and transport information across distances that dwarf human comprehension. The comet served as translator between stellar systems, carrying news of distant nucleosynthesis and alien chemistry, written in the universal language of atomic structure and molecular bonds. The stillness that follows its departure contains all the patience of geological time, where events unfold across scales that make mountain building seem rapid and continental, drift appear hurried. In this vast temporal landscape, the next interstellar visitor may already be en route, carrying its own cargo of mysteries across light years of emptiness toward a future encounter with telescopes not yet built and minds not yet born. The universe continues its slow conversation between stars, each message taking millions of years to compose and millions more to deliver, creating a dialogue that spans galactic distances and operates according to rhythms older than planets. The darkness listens and remembers, holding in its silent depths the scattered remains of countless objects that have completed similar journeys between stellar systems. Each contributes its microscopic legacy to the growing inventory of processed materials that circulates through galactic space, creating the chemical foundation for future generations of stars and planets. In this vast recycling system, endings become beginnings, and dissolution serves creation. Sleep comes easily in such immensity, where individual concerns dissolve into the larger patterns that govern cosmic evolution. The gentle breathing of stellar nucleosynthesis continues in countless cores throughout the galaxy, creating tomorrow's heavy elements from today's hydrogen and helium. Gravity shapes and reshapes the distribution of matter according to laws that operate with perfect consistency across scales ranging from dust grains to galactic superclusters. Rest settles over the spaces between worlds, where the remnants of ancient visitors drift through darkness deeper than any earthly night, carrying their molecular memories toward destinations that will not be reached for millions of years. The universe sleeps fitfully, dreaming of future encounters between matter and light, between the debris of dead stars and the gravity wells of living worlds,